right. I mean, a deconvolution network is again, right. I mean, except that because, right, that idea of trying to sort of, right, draw the outputs of the previous pooling layers and then fusing in order to be able to get the output was not really a smart idea. So it is more like a formal approach. So a deconvolution network usually will use what is called a transposed convolution. You guys know about transposed convolution, right? So transposed convolution is like this. So what this means is, right, see, if I have how to explain this. So if I have Ax equal to y, if you do a convolution operation, right, think of x as a let's say, right, this is your forward path. That means you are doing a convolution with some stride, okay, and which means that x is of a higher this one dimension, and then you are going down, okay, doing a strided convolution. So what will happen? So when you actually construct this matrix, so suppose x is a 4 cross 4 sort of a feature map, okay, suppose it's 4 cross 4, right, then this will be this, you can stack it up as a 16 cross 1 vector. I mean, you can write it in a vector matrix vector form, and y, right, the output, suppose let's say you are doing a strided convolution such that the output is actually a 2 cross 2 output. Okay, suppose, right, then it means that if you stack this y up, it will be a 4 cross 1 vector is what you want to get, and therefore this A will be something like 4 cross 16, right. That will be the matrix that you will have to build. Now, see, there's an easy way to just say, in a sort of illustrative way how to actually arrive at this, but then the equation part is important, okay. That is just a graphical illustration which I will tell in a minute. Hey, by the way, right, I know that I have exceeded, but I just wanted to tell you that, I will just continue until I finish this topic today, and let me also tell you one more thing. Right, this Wednesday again, right, again I am not available this Wednesday, unfortunately, and Tuesday is a holiday tomorrow, right, tomorrow is a holiday, correct. So the next class is only on Friday, and since today is the last instruction day, after this, right, I don't even expect you to come. I mean, right, I will encourage you to come, but then it's not a must that you have to come. I have actually 2 more classes to go. I am taking one on Friday and one on Monday. I will be here, I will record this session, right. I mean, you are of course, right, encouraged to come, but I am saying that I will not take, say, attendance, okay. So the last 2 classes I will not take attendance, but of course, right, I will be happy to see you guys here. If you don't come, it's okay, okay. So there is still, because the high level vision, I want to talk about RCNN and all, YOLO and all that, right. So I thought I will take, and there I may even exceed my time, because, right, I talked to Mahesh and he said it's perfectly okay, it can be done, because that once I upload the video, you guys can then watch it later. Okay, but I want to finish off everything by 14th. That was my initial target. This thing was unexpected. The last week, one day I lost, and then this Wednesday I'm losing again this game due to some unexpected something else, right. So I couldn't, beyond my control. So I wanted to finish by this Friday, but that's not going to happen. So Friday, Monday, and then maybe one more day. Okay, so those 3 classes, right. You are of course, absolutely right about, it will be great if you can come, if you can attend. If you cannot attend, it's okay, right. I will record it here and I will upload. I just wanted to tell you that, and now also, right, I may take another 5 minutes. If you have something, you can go. If you have a class or something, okay.
Ground truth, how are we generating?
Where? Oh, segmentation. No, this is all hand annotated. This is all annotated. There are these people, right, that are paid for it. So
it's very like structured, right? Like for example, there may be many more images in this data set. And if some other image has that cow in that picture, that same color should be given.
No, it's just a cow, that's all. It can be of any color. A cow is a cow. Okay, so this upsampling thing, right? So it's called so downsampling, of course, is typically a strided. So what I was trying to say was this kind of a transpose convolution, right? So what this means is, you see, what will happen is, you're doing kind of a downsampling, then you're going, in an upsampling path, right? Now, if you have done a certain sort of a strided convolution at the, let's say, 4th layer here, right? Then after you reach a bottleneck, then you go back. Then in that 4th, in the upsampling path, right, when you come to the 4th block, right, you want to be able to use the same A transpose, right, so that whatever size was here, you actually meet that size back again here. Now that's where, but then the features would have changed, right. I mean, you don't get the same X now, you'll get some other feature. The idea is that you take A transpose, you can show this, okay, this can be mathematically shown. You take A transpose, which is actually 16 cross 4, and then you operate it on that let's call that Z. It doesn't have to be Y, right, it will be some 2 cross 2 feature map there, right, which you want to get a blow up to 4 cross 4. Understand this, right? Somewhere you had a 4 cross 4, and then right, it came down to 2 cross 2. On the upsampling path, you have a 2 cross 2, it needs to be blown to 4 cross 4. So the A that you used here, now you need an A transpose. So whatever you did here, right, you want to sort of undo it, but it is not strictly speaking A inverse, okay. So please do not think of deconvolution as some inverse of the convolution at all. It is simply an operation. So it simply spreads values. I mean, that is a way to kind of think about it. Okay, I mean, so sitting at a place, it spreads the values, right, in a certain sort of a proportion. So A transpose will act on Z, which is actually 4 cross 1, in order to give you, let us say, some other whatever P or something, which is actually 16 cross 1, which is 4 cross 4, right. That is how you go. So that is why it is called a transpose convolution, and if you think about it, right, this is how it will look. Sorry, this is max pooling, right. See, transpose convolution actually, okay, I mean, think of this kernel as or change some values. I mean, I do not know why they have given the same thing, right. So let us say you got A, B, C, D, right, as the input. So what will happen is when you have kernel, when you actually do this transpose convolution, I mean, mathematically if you do it, that is what you should do. Graphically how they show it is, so for the first case, right, you will have 0 0 0 0 because this guy is 0, and then for the second case, right, when you have 1, okay, so what you will have is like A, B, C, D here, okay, and then when you have 2, right, you will have like 2A, 2B, 2C, 2D, okay, and then right, when you have 3, right, then you will have like 3A, 3B, 3C, 3D, right, and all this you have to add. Spatially, right, there will be some common entries also, right. For example, right, this 2B and then C and then whatever, right, 3A, they will all add up, right. Yeah, that is fine, like I told you, you can go. Okay, so once you sum it up, then you kind of get your output. This is exactly the same operation, right. If you did A transpose on this 2 cross 2, which is this input and that kernel, this is exactly what will happen. Okay, but then this is how graphically people, right, illustrate it, but it can be mathematically done properly. Okay, now the max pooling, max unpooling, you people know, right, how it is done. So that is typically like this, right. When you want to do max unpooling, so what you do is, if you want to do an unpooling, so you kind of, so in this case when you are doing max pooling, what did you do? You pick the, so here is kind of a pooling, a 2 cross 2 pooling with a stride of 2, right, or 2 cross 2 filter with a stride of 2, that is what it is. So here you get 5, here you get the max value is 6, max value is 7, max value is 8. Now when you go back, right, you may have some other feature which is 1, 2, 3, 4. Now you want to do one max unpooling. So the one will go and sit exactly, so this you have to store somewhere when you do max unpooling. So you have to know that location from where the max was picked. So that is something that you have to carry with you, and then you place your 1 there, you place the 2 exactly right in this location where 6 was, 3 will go wherever 7 was, and 4 will go wherever 8 was. And now after this you followed up with a bunch of convolution kernels which are actually learnable, and then because you do not want so many zeros sitting there, right. So basically they will start filling up all these zeros. Now,
why does position matters?
because when you do want to do the back prop, you need to kind of, right, back prop through those points, because those are the ones from where you pick the max value. So this is for the back prop. Sorry? No, no. The point is this is the simplest way in which you can do max unpooling. I mean, if you had this information, you can do the unpooling. If you don't have, how will you do it? Because you should know from where the max was picked. You won't know. You have to have it. Max unpooling will require that you know the location. In fact, it's always done a standard thing, and you know from where you're coming. And then this transpose convolution, right? That's how it works. Then okay, so this deconvolution network, and here are some examples. So that's the only sort of a takeaway, right? So instead of doing it in that arbitrary manner, right, you do a proper sort of a transpose convolution here. Okay, and then they show some output results, right. So here is a cycle, and you can see that it's picked up the wheels correctly, and then right, it's actually segmenting the cycle well. Of course, there could be some sort of a confusion here and there, but then the segnet is exactly the same way. Okay, so we don't talk about segnet, in separation. It's basically the same logic, and in fact these are all papers that came around the same time. Therefore, right, I mean, it's not like one guy took the idea of the other man or something. So it's actually it's a contemporary kind of work, right. And then deep lab is the last one that I wanted to talk about. So here, so the idea is that, right, so deep lab is nice because it doesn't even want to kind of reduce your spatial resolution. So it wants to operate exactly at the same sort of resolution at which the input is. All the other methods that you saw were initially downsampling, then upsampling, right, which means that you are already losing some information which you are trying to kind of recreate later, and then there is every possibility that you have lost something along the way. Therefore, the way they kind of do it is, in order to not kind of lose resolution, is they use what is called as at-rest convolution, or what is called really a dilated convolution. So this dilated convolution again kind of, see, why did you do this downsampling in the first place? Because you wanted a receptive field, right, which was higher, or it would have meant that you would have used multiple layers, so that a kernel, right, will actually, instead of looking at 3 cross 3, it will effectively look at 5 cross 5 or 7 cross 7. That's what you ideally want to do. But at the same time, right, they did not want to have these computations going up, right. So they wanted a receptive field which is higher, and then the computations should also not go up. So which is the reason why they kind of came up with this. Say at-rest convolution was already there. So and then there is a pyramid pooling, and they just put the two together. So at-rest convolution looks like this. So you have a 3 cross 3 kernel. So if you have a rate 2 at-rest convolution, what that means is that simply you fill zeros everywhere else, and then you simply place these, like, every third. So it's like 1, and then 2 third, you again pick the pixel. Sorry, second. So 1 2, that's why it's called a rate 2. 1 2, then 1 2. 1 2, right. I mean, that's how you place. I mean, every alternate row and column, right, you kind of take it's the same values. So you don't have to learn anything new. It's simply still 3 cross 3, but now your receptive field is over 7 cross 7, right, in a way. And then the fact is, the in between there are zeros because they don't want to increase the number of unknowns, right. I mean, then it won't make sense, right. So the idea is that with this actually it works very well, and then you can have a rate 3 whatever, right. So the idea is that with these kind of filters, right, you can have a receptive field that can go up, and therefore you don't have to reduce the image size, right. You can still have a receptive field, that's good. And then alongside came the idea, there was this spatial sort of a pyramid pooling which is already there. I mean, if you kind of remember it in CNN, suppose I told you that I mean, what would you do if you had to train with different sizes of inputs? Can you actually train it? Well, suppose you had a classification layer somewhere, right, at the end, and then let's say you have CNNs in between, and then I have images, right, or no, which I want to feed to this network. So you saw that all the way AlexNet, what was the size? It was always fixed, right, some 224 something cross 224. Why did it have to be like that, right? Simply because we weren't accommodating for the size somewhere. So the spatial sort of a pyramid pooling does exactly that. So what it will do is, irrespective of whatever the feature map size, it will always kind of bunch it into say 16 zones. So in this case, right, for example, right, I just divide it. So if it is higher, then each block will then be larger. If it is smaller image, each block will become smaller, but I still get a 16 sort of, so for each of these I'll get one value, for each of these I get one value, I get 16, and then if there are 256 feature maps, I get 16 cross 256 kind of right, I mean this one, a vector. And similarly, right, I can have 4, instead of dividing into 16, I can have 4 blocks, I can have just 1, right. So that's the idea of spatial pyramid pooling. So which means that whatever be the input size, right, eventually what comes out of this fully convolutional network is finally one standard size which comes out, which means that I can accommodate any size, right. That's actually a good idea, I mean, right. So it lets you operate with images of various sizes and so on. So that's the spatial pyramid pooling. No, see, what this means is, if there are 256 feature maps, and each one, these are all of the same size, but then, right, these could come from, a different image size would mean that my feature size is then kind of different, because there is a subsampling ratio that you maintain, right. Even if a convolutional network, there is a subsampling ratio that you maintain, but the size will change, right. So what this is saying is, if I have a larger image, I will, whatever be the image size, I will divide it into a certain number of blocks, in this case 4 cross 4. So which means that for every block, I'll pick one value. It will be like a global average pooling for that block. I'll get one output. So I always get 16 cross 1, irrespective of whatever be the size. Then I can change it. I can have 8 cross 8, I can have 4 cross 4. I can have. So that's called. And then the pooling comes because they don't just do it with one resolution. It's like a resolution of the block. You can have a coarser resolution. You can have a very coarse resolution, and then you concatenate all of them. That's why it's called a pyramid pooling, a pyramid, because you have like 16 cross 16, 4 cross 4, that's how you saw that, no, when you saw a Gaussian pyramid, I mean, what was that? So similarly, a pyramid and then pooling, right, because all these vectors will then be pooled together in order to create one sort of a flattened out vector, which will remain the same dimension irrespective of whatever comes in, so that after that, right, you can operate whatever you want, right. That's the biggest advantage of say, SPP. And now these guys smartly combine both, right. So this parallel pooling idea is this, right, where you have different rates. So here the way they pooled, they kind of did this, they call it spatial pyramid, at-rest spatial pyramid pooling, I think ASPP or something, and the idea is that they do of course this at-rest convolution, but then because they operated at say different rates, right. So for example, rate is equal to whatever 18, 24, so they operated different rates, then they take all these, so there is a parallel set of filters acting, right, a parallel set of filters acting, right, seeing different parts of the image, and then all of them getting fused, right, in order to be able to get your final output, right. So that's the, and Deep Lab is apparently one of the best that is still around, okay. That's why I thought I should cover this. and you can see this, right. But then this by itself does not work so well. There is still one final thing that they have, which is a conditional random field, right. I mean, that by itself gives out sort of a smoothed output. So the whole paper is not just that. Then there is a post processing after the network. This is not part of the network. So that's a conditional random field, because right, you guys haven't learned Markov random fields and all, right. So I can't go into the details. But then what this means is that if you think of an image as a graph, or you think of the output as a graph, right, where you think of each kind of pixel as a node, and then you have edges, right, to kind of to every other node. Okay, you don't have to every other node. You can have a small neighborhood around which you have nodes, edges, and then the weight of the edge will tell how important, right, is that is there other label for this label, what kind of a dependence, right, it has. Actually, there is a whole area called graph based segmentation, right, which we could not take, and because these are the idea is that deep networks having come now in full flow, right, people are no longer going that way. So there is no point in doing all of that, because right, eventually you will end up doing only probably one of these things, right. So I thought classical, I wanted to give you a feel for what are the general things. There are various methods, even there is something called region based growing in segmentation, this graph based and all that. But anyway, right, so kind of this comes from somewhere there, right. So where you have something called a unary term, then there is a pairwise term, and then how these pairwise terms should sort of what weights, right, they should get depending upon how close they are, right. I mean, and there is a weight for, I mean, there is this kind of exponential quantity here, right, which is in terms of the location, and then in terms of the feature value and so on, takes all of that into account to arrive at something like an energy minimization. So the energy minimization is something that will keep coming, okay, that is all spread all over, and typically there are standard ways to kind of do it, and that's what, right, they have done. But what they showed was eventually that using the CRF, right, things become really better. So here, right, if you see, right, because CRF is actually an iterative process, so with every iteration, right, things improve until you get down to something like that, right, which looks very good, right, as compared to what they started off with. Okay, and that is what is Deep Lab, and with that, right, we are done with segmentation.